Hello everyone, this is Professor Roman. Let's continue the group theory lectures. Now it is time that we address an important structure theorem for groups. A structure theorem is a theorem that says that a particular family of groups has a particular structure or form. That could be as simple as, what do the groups of order 12 look like? What is the structure of those groups? And as we'll see later in the course, and as I've discussed before, there are 5 non-isomorphic groups of order 12, and so we have a structure theorem for groups of order 12. Every group of order 12 has one of those 5 structures. On the other extreme, we could have a structure theorem for all groups, which I think we are a very long way from having. But now we have enough group theoretic machinery to find a structure theorem for finite abelian groups. And that in itself is quite an achievement. We will see that any finite abelian group can be decomposed into an internal direct product of cyclic P subgroups. And we're going to do this in 2 stages. First comes the primary decomposition, and then will come the primary cyclic decomposition. The primary decomposition is relatively straightforward. The other one is rather more subtle. So let A be a finite abelian group of order n. And let n have this prime factorization. So P1 through Pm are primes and they are distinct. For each prime, P sub I, we define this set A sub P sub I to be the set of all elements of the group that have exponent pi to the ei. That's the same set as the set of all elements of the group that are pi elements together with the identity. This is easily seen to be a subgroup of A because A is abelian. If you have 2 elements of exponent pi to the ei, their product also has this exponent. Now the integers qi, which is the order of the group missing one factor, one prime power, pi to the ei, take that one out, call that qi. These integers are relatively prime. They are not pairwise relatively prime, but they are relatively prime. And therefore Bezos' identity tells us that there exist integers, j sub I, for which this linear combination of the q's is equal to 1. Therefore, if we take any element of A, we can write it as A to the power 1, which is this. We can then split this up into this product. Now, A to the Q1, for example, has exponent P1 to the E1, because if you raise that P1 to the E1 power, multiply by Q1, you will get the full order n, and that will annihilate A. And the same is true, of course, for the others. So this element belongs to this set product of all of these subgroups. And this element was an arbitrary element of the group, and so A is equal to this set product, or join. It's the same thing because the group's abelian. Moreover, this set of subgroups is strongly essentially disjoint. because if an element belongs to API and also to the join of the other subgroups, then this membership tells us that A has exponent pi to the ei. This tells us that A has exponent qi, but those are relatively prime. And by an argument I believe we did once before, I mentioned before, if you have an element that has two exponents that are relatively prime, that element has to be the identity. So the intersection of API and this join is trivial. The family is strongly essentially disjoint, this family of APIs, and therefore A is an internal direct product of these subgroups. In summary, and this is called the primary decomposition of a finite abelian group. Let A be a finite abelian group and its order is factored. This is the prime factorization of the order. So these primes must be distinct. Then if we define API this way, A is the internal direct product of these subgroups. The order of API is pi to the ei, and the subgroups API are called the primary factors, or primary subgroups of A, and this decomposition of A is called the primary decomposition. The primary decomposition of A is unique up to the order of the factors, which we cannot control. So what this means is that if not only if A looks like this, but it also has this decomposition where the QIs now are prime. Now, these QIs are not the same QIs that I defined over here. Once we finished this analysis, those QIs went away. So I probably should have used a different letter, but it didn't occur to me at the time, frankly. So these are just, Q1 through Q are just primes, distinct primes. And if each of these subgroups is a QI group, then the uniqueness tells us that there are the same number of factors in both of these decompositions, R equals M, and after reindexing the primes, if necessary, these Qs, we can align them with the other decomposition. So Qi equals Pi and BQi equals API for all I. So we've proven all of this except the uniqueness part. But if we do have both of these decompositions, the original one we found and another one somebody else found, let's say, then we can compute the order of A using both of these decompositions. It's the product of Pi to the EIs, but it's also the product of the QIs to the FIs. And, well, an integer only has one prime decomposition, one prime factorization. So R and M have to be the same, and after reordering, the PIs have to match the QIs, and the exponents have to match. And that's the uniqueness. The primary decomposition is the first step in unraveling the structure of finite abelian groups. And the next step is to show that each of the primary factors, A sub pi, in this primary decomposition is the internal direct product of cyclic pi subgroups. So we need to show that API is the direct product of cyclic subgroups. They will be pi subgroups because everything in this group has order of power of pi. The indexing here is getting a little nasty, double subscripts. The first subscript is I, it matches the prime p sub I. The second subscript has to involve I, and so it's m sub I, because for different pi's we may have a different length in this direct product. So this depends, the length, the number of factors here depends on the prime. So to cut down on some of the baggage here with subscripts, we can just assume that we have a finite abelian group A and it's a P group. So once we show that that can be decomposed into cyclic P groups, or P subgroups, then we can apply that to each of the primary factors in the primary decomposition. And then we won't have to deal with the double subscripts. Now our goal now is to show that we can, you might say, peel off a cyclic subgroup and write A as the direct sum of a cyclic subgroup, here generated by U1, and a direct complement of this cyclic subgroup, which we'll call X1. Now, if we can do this, then since X1 is also an abelian P group, we can do it again. We can peel off another cyclic subgroup, assuming X1 is not trivial, and get another direct complement X2, and we can just continue to do this. And because everything is finite, this process will stop when the direct complement is itself cyclic, and then we'll have a direct product of cyclic subgroups. So all we have to do is master this peeling off business. And this is the real tricky part of the entire characterization of finite abelian groups. So here is the theorem. Let A be a finite abelian P group. If an element U in A has maximum order among all the elements of A, then there is a subgroup X for which A is the direct product of the cyclic subgroup generated by U and X. This is the peeling off. And what follows from this, as we just discussed, is that A will be the direct product of a finite number of cyclic subgroups. The order of UK is going to be a power of P to the EK. These orders, P to the EK, they don't have to be distinct, and that's very important to keep in mind. They are called the elementary divisors of A. And this decomposition is called the cyclic decomposition of A. The order of A is then the product of the elementary divisors, because those are the orders of the factors in this decomposition. It's customary, not required, but customary, to arrange the elementary divisors in decreasing or descending order of size. So that applies, since the base is always p, we can just apply it to the exponents. Okay, so we'll assume that that's generally done. It's a matter of style, a matter of convenience, really. Now, the cyclic decomposition, unlike the primary decomposition, is not unique. But the multiset of elementary divisors, and it is a multiset because, as I said, some of these elementary divisors may be equal. The multiset of elementary divisors is unique. In that, if we had another cyclic decomposition, then the product, so let's say this is the cyclic subgroups generated by V1 through VR, and the order of VK is P to the FK, then R has to equal M, and after re-indexing, if necessary, the FKs are the same as the EKs. I probably should point out here that, this is not the prime factorization of the order of A. Okay, it's true that A is a P group, so it only has, all of its elements have order of power of P. But this is just the product of the elementary divisor. So I don't confuse this with, if I can find it here, with this prime factorization. Okay. This is just the product of the orders of the factors. And some of those may be the same. Okay, now let's tackle the proof here. And you might need to fasten your seatbelts on this one. I have tried multiple times to rewrite this proof to make it as motivating, I suppose you might say, as possible, to make it somewhat clear that what the next step should be. But frankly, I have not had much luck. So this is the best I've been able to do so far. And one thing that I did do is emphasize the role of the extreme witness principle, which we talked about before. And you'll see that appear a couple of times in this proof. Sometimes when you don't know what to do, you say to yourself, let me find an extreme witness to something, and maybe that'll give me a clue where to go next. Now, we're working on this peeling off of this cyclic subgroup here, where U has maximum order among all the elements of the group. And to simplify the notation a little bit, I'm going to denote this cyclic group by capital U. I debated whether that makes sense or not. The more notation you introduce, the more you have to remember. But this is just an awkward set of symbols, and it tends to get in the way, so I decided to do that. And suppose that the order of U is P to the M. That has maximum order. Okay, now we need the direct complement of this subgroup U. We need X, capital X. It has to be essentially disjoint from U. Where shall we find it? Obviously, among the subgroups of A that are essentially disjoint from U. Well, the trivial group is, but that's obviously not going to work. What we need is a subgroup that among the subgroups that are essentially disjoint from U, one of maximum order. That's the best hope for getting this, let me bring it back again, for getting this direct sum decomposition. I want x to be as large as possible in the hopes that this direct sum is actually all of A. So that is an application of the extreme witness principle. Okay. So was the choice of U an element of maximum order. So I didn't even say that, but that was really the first application of the extreme witness principle. This is the second one, and there's going to be a third one. Okay, so we take X to be of maximum order among all subgroups of A that are essentially disjoint from U. And we want to show that X satisfies, well, once again, that X fits this equation here. So suppose it doesn't. Suppose that this direct product is strictly less than A, is a proper subgroup of A. This is the same as the set product. Okay. Because we know these are essentially disjoint. So this is the set product. Now, what to do? Well, let's apply the extreme witness principle again, looking at the elements that belong to A but do not belong to the set product. Now, and there's two ways you might go here. You could pick one of maximum order, or you could pick one of minimum order. I don't know whether picking one of maximum order is going to do much good, but I do know that picking alpha here that has minimum or smallest order among the elements of A that are not in UX will be good. It will help. And so that's what we'll let alpha be, and we need to find a contradiction because this assumption is what we want to contradict. Now, the reason the smallest order element works, a smallest element order works, is right here. The minimality of the order of alpha implies that alpha to the p, which has order less than alpha, is in UX. And so alpha to the p has the form u to the power I x. I is some integer, x, little x here is some element of capital X. Now, we had a theorem way back in Chapter 2 about the orders of elements in abelian groups. We talked at length about element orders. In an abelian group, the order of every element divides the maximum element order, which is p to the m. So the order of A divides p to the m. So this is where we stand at the moment. We have this expression for alpha to the p, and we know that the order of alpha divides p to the m. So this would suggest that we raise both sides of this equation to the power p to the m minus 1. And that will give us p alpha to the p to the m, which is 1, is equal to this. Doesn't look very pleasant, but this is in capital U, this is in capital X, and they are essentially disjoint, and so they both have to be equal to the identity. We don't care that x to the p to the m minus 1 is the identity, because we don't know anything about x. It's just some x in capital X. But we know more about U. We picked it to be the element of an element of A with maximum order. So this is the one we're interested in. U to the I, p to the m minus 1 equals 1. u has order p to the m. If this is going to be an exponent of u, then p must divide I. There must be another factor p in here to get to p to the m. Therefore, this expression for alpha to the p can be written this way. Alpha to the p equals u to the jpx, where j is some integer. And so we can rewrite this by isolating little x, of which we know not, except it belongs to capital X, and deduce that this belongs to capital X. Okay, I don't know about you, but I'm already thinking, where's all this stuff coming from? I don't know the answer to that. But the way you can look at this is we are just fiddling, coming up with ideas that give us equations and membership relations and hoping that it will lead somewhere. I know that's kind of a pessimistic point of view, but I just don't see the clear path here in this proof. All right, so this is where we are now. And now we might notice that alpha u to the minus j inside here, this does not belong to capital X. Because if it did, then alpha could be written this way, and this would be in ux, but alpha was chosen specifically to have minimum order among the elements that are not in ux. So we know that the power of this thing here is in x, the pth power, but that it itself is not in x. Now again, I'm going to hopefully improve the readability here by denoting alpha u to the negative j by beta. And so what we have is beta belongs to x, but beta to the p, beta does not belong to x, but beta to the p does belong to x. Okay, what to do next? Well, one thought is that we have not yet used the maximality of x. If you get to a point in a proof and you kind of don't know which way to turn, it's worth reviewing what you've already done, hypotheses of the theorem, facts that you know or are allowed to assume that you haven't used yet. Presumably they're going to be needed, they need to be used at some point. Maybe this is the point. So, since beta is not in x, the subgroup generated by beta and x is strictly larger than x, and therefore it must intersect u non-trivially. And so there exist positive integers n and r and an element little x in x for which beta to the n x equals u to the r. This is an arbitrary element of this subgroup. It's a power of beta times an element of capital X. And it's then, if it's going to be in u, it's also a power of u, and if it's going to be non-trivial, this is not equal to 1. What does this imply? Well, beta to the n cannot be in x, because then this whole side would be in x, but this is in u, and x and u are essentially disjoint. And this is non-trivial. It's not the identity. Beta to the n, however, is in ux, if we move this x to the other side. So we got two more facts. We collected these two facts, and now we've collected two more, and here are all four of them. And so we sit and stare at this. and say, are there any combinations of these things that are going to tell us something? And I guess you guessed the answer is yes. Beta to the p belongs to x, that's this one, but beta to the n does not belong to x. Therefore, n cannot be a multiple of p. P cannot divide n. P is a prime, so p and n are relatively prime. And that should give us a little smile, because when you stumble upon two integers that are relatively prime, you kind of know what to do next, and that is appeal to Bezos' lemma. So there are integers r and s for which rn plus sp is 1, and so alpha u to the negative j, which is being written as beta, is equal to beta to the rn times beta to the sp. Where is beta to the rn? Well, beta to the n is in ux, so beta to the rn is in ux. Where is beta to the sp? Well, beta to the p is in x, and therefore in ux as well. And so alpha u to the negative j is in ux. Now we move the u to the other side, and alpha is in ux. Contradiction. Okay, so that's the proof, or that is a proof of the peeling off process. We now come to the uniqueness part, and it's not the uniqueness of the cyclic decomposition, it's the uniqueness of the multiset of elementary divisors. So suppose that we have two ways to decompose, two cyclic decompositions of A. The order of uk is p to the ek, the order of vk is p to the fk. And again, we'll assume that the orders are in descending order of size. The order of the first factor is p to the e1. It is the maximum element order in A, p to the m. Okay. Similarly, the order of v1, or this subgroup, p to the f1, is also the maximum element of order. So they're equal. And so E1 equals F1. These are cyclic subgroups, or cyclic groups. If they have the same finite order, they are isomorphic. Okay. Now we see why the cancellation theorem was so important, why we spent time dealing with proving the cancellation theorem. We have an equality of these two, of these two direct products. The first factors are isomorphic. This is what I called, at the time we discussed cancellation, the internal equality version of cancellation. We can cancel the first factors here. A1 is the product of the other factors involving the u's. B1 is the product of the other factors involving the v's. These, by cancellation, these are isomorphic. We lose the equality. If you look back at the cancellation theorem, we lose equality. But it doesn't matter. When we look at this, p to the e2 is the maximum element order in A1. P to the F2 is the maximum element order in B1, But A1 and B1 are isomorphic. They have the same element orders. So F2 equals E2. And then again we can cancel. Now we're using the internal isomorphism version of cancellation. But that will obtain from now on. We lost the equality the first time. The rest will be isomorphisms. And so as we continue to do this canceling, we can't run out of one side before we run out of the other side. So m equals r, and all the exponents are equal. And that's the uniqueness part. Now we can put the primary decomposition and the cyclic decompositions together and completely describe the structure of finite abelian groups. And here is the theorem. This is now the primary cyclic decomposition of a finite abelian group. So A is our abelian group. Here is the prime factorization of the order of A. Here are those subgroups we used earlier to get the primary decomposition. These are primary subgroups of the group A. Each of these primary subgroups has a cyclic decomposition. And so when we do the replacement here, we get a decomposition of A into a direct product of primary cyclic subgroups. They're cyclic PI subgroups. So the order of Aij is Pi to the Eij, and these do not have to be distinct. Obviously for different primes they will be, but for the same prime, Pi, the exponents, some exponents may be the same. These integers are called the elementary divisors of the group A, and this decomposition is the primary cyclic decomposition of A. The product of all of the elementary divisors is equal to the order of A. And again, it's customary to arrange the factors within each primary subgroup in order, in descending order. These are the elementary divisors with the same prime, the same base. The multiset of all these elementary divisors is unique. All primary cyclic decompositions have the same multiset of prime power orders, or elementary divisors. The multiset of elementary divisors is then a complete isomorphism invariant. So it solves the classification problem for finite abelian groups. Namely, two finite abelian groups are isomorphic if and only if they have the same multiset of elementary divisors. Now, this is a theoretical result, not a practical one. Finding the elementary divisors is, for the most part, impossible. For small order groups, we can do it. But remember where it all starts, with the prime factorization of the order of A. Even that, we don't know how to factor large integers in any efficient way into products of primes. We know there is a factorization, but we don't have an efficient algorithm for doing so. So this is a theoretical result in general terms more than it is practical. Okay. There's not much left that we have to prove, The uniqueness follows from three facts we've already established. Two primary cyclic decompositions have the same primary components, or in other words, there's only one primary decomposition. All cyclic decompositions of a primary component have the same multiset of elementary divisors, and so because the multiset of elementary divisors for the whole group is just the union of the multisets of the elementary divisors for the primary factors or components, we know their union is unique. The final part is the complete isomorphism invariant. I'm going to leave it to you to show that two finite abelian groups with the same multiset of elementary divisors must be isomorphic. For the converse, if we have an isomorphism from A to B, then then B is equal to sigma A, and sigma goes all the way inside the direct product and inside these angle brackets, and so the a primary cyclic decomposition of B looks like this. One of them looks like this. But applying sigma doesn't change the order of the elements. So we get the same elementary divisors here that we got from the decomposition of A. This theorem is remarkable. And what is also remarkable is how far we have come in 179 pages of this book since, and even in less time, since we first defined the concept of a group. We now understand the nature of finite abelian groups. So let's look at an example of what we can do on a practical level with this result. Suppose that we want to consider the groups of order 72, finite abelian groups of order 72. It has this prime factorization, 2 cubed, 3 squared. The elementary divisors associated with a base of 2 are powers of 2 written in descending order, and E1 here lies between 1 and 3. It can't be bigger than 3, because remember that the product of these has to be 2 cubed. Similarly, we have the elementary divisors associated with the base 3, and the sum of their exponents has to be 2. So we have these two constraints placed on these exponents. And that severely restricts the possibilities. For the base 2 elementary divisors, E1 could be 3, and we just have one elementary divisor. E1 could be 2, E2 could be 1, we'd have 2 elementary divisors. Or E1, E2, and E3 could be 1. We have 3 elementary divisors, and similarly, we get these two possibilities for the base 3 elementary divisors. There are a total of 6 possibilities. In this case, if we take the first 2 sets of elementary divisors, we have, remember, 2 cubed here is the order of the first factor in the decomposition, order 8, cyclic, C8, C9. Or if we take this, well, it's not a multiset, this set of elementary divisors, this multiset of elementary divisors, we get C8, direct product C3, direct product C3. And you can check the others. So here are all 6 possibilities. If I can get them on the camera, there we go. And we have characterized all finite abelian groups of order 72. They are all isomorphic to one of these 6 groups.